Today in this video we are going to discuss about acceptor or p-type semiconductor. In the previous video we discussed about donor impurity atoms and how you can add donor impurity atoms to create n-type semiconductor. So in this video we are going to talk about acceptors or acceptor or p-type semiconductor. P-type semiconductor. So what we are going to do to create a p-type semiconductor, p-type extrinsic semiconductor. So suppose you have a intrinsic semiconductor, intrinsic material, intrinsic semiconductor like silicon or germanium, okay, and then you add impurity to it. So what kind of impurity we are going to add here? So if you will add a group 3 element, okay, so group 3 element such as you can add boron, okay, or add aluminium. These are all trivalent or group 3 elements. So aluminium, or you take gallium or indium, okay, these are the materials, okay, these are the elements that belong to group 3 and these are trivalent impurity. So this trivalent impurity, as we know, will have 3 valence electrons, okay. Now if we take silicon, like we said, is a tetravalent, so you have like electrons here in the outer orbit, you got 4 valence electrons like this. Now if I'm adding a boron to it, okay, so which is trivalent, we said we'll have electrons like 3 valence electrons here, right? Now what you will, the same way like we had discussed, okay, these electrons here, okay, they will all like share the electrons. These atoms will share their electrons to form covalent bonds. So what we got here, you can say this electron will be added up with this electron with this one, and this third electron with this one. They will form covalent bond, okay. So all these, 3 valence electrons are taken up in the covalent bonding, right? So only one electron you can see here, this particular electron is left out now. Okay, it is not forming any covalent bond. Okay, but what happened here, now it is available for the covalent bonding, right? So here, so one covalent bonding position is likely to be empty, okay, here. So it can accept one electron. So if an electron were to occupy this empty position, like if you just take, like, for example, here silicon and your boron you got, suppose silicon and boron we got. So one electron here, let me use some other color. So electron here you got, and here you got some empty position which can be taken up, right? And all other electrons, like we got, this electron here and this electron here, they form the covalent bonding. You can see, here electron, this electron, another electron, taken up. Okay, so like, taken up here, one electron here, okay, one. Similarly, some other electron here, like, this electron, and over here another electron here, they are also taken up or in the covalent bonding. Okay, now what do we said? If an electron were to occupy this particular empty position here, okay, its energy would have to be greater than that of what? The valence electrons. Okay, its energy should or energy would have to be greater than that of the valence electron, right? Then only it can take. Okay, so in the band structure we can do that actually. Okay, in the band structure what we can do is, suppose we have the conduction energy band, we said EC, and then you have the valence band here, right? So we said that the electron which is there is one space over here, okay, and there is a space for another electron to come here to make that covalent bonding happen, right? And the amount of energy that is required here, okay, the amount of energy that is required is definitely very very small. Okay, this process actually, if you'll see, the trivalent impurity has a tendency to accept one electron, as we said, because you can see as there is one electron deficiency, right? So from some neighboring atom, it can take one electron to form the fourth covalent bond, right? and the amount of energy required for this is very very small. And the same way like we did, we consider it in case of donor impurity atoms. The same way here you can also say the energy required is very small, okay, which can be provided by a thermal agitation. A small thermal agitation in the crystal, okay, can provide that amount of energy to some electron from the silicon atom to come and fill that particular space that is available, okay, when a trivalent impurity is added. Okay, so now what we got actually here, so you when you are adding like these trivalent impurity atoms, or we said the group 3 elements such as boron, aluminum, gallium or indium, right? So these acceptor, they can accept one electron, right? You created acceptor state here. So that acceptor state must correspond to some energy, some finite energy value, and we will denote it as ea, so the energy that corresponds to this acceptor level. So any electron, okay, which will move from this valence band, okay, valence band, and will go to this acceptor state, will require some amount of energy here, okay. So require some amount of energy. So what is that that energy that is required? If you see the order of this is actually around 0.01 electron volt, okay, above the top of the valence band. So here if you'll see, this value is actually 0.01 electron volt, is it's approximate value 0.01 electron volt, okay. So now this is the order we said, okay. Now this acceptor state will take this electron. So similarly, you have more acceptor states, then with thermal agitation or very much small amount of energy if you give to the crystal, then all these electrons which are there in the valence band will now move to this. So what we got, we can see now, here these electrons, okay, from the valence band are moving to the acceptor level. Okay, now what you got here, okay, what you got here, here you got these electrons, okay, these electrons, okay, received by this boron or group 3 element, okay. These are the immobile ions, just like we consider in case of donor atoms, immobile and fixed ions, okay. So these immobile and fixed ions, they are not actually contributing to the process of conduction. But what you got here are the holes. Because of what? Deficiency. Because of what? The electrons are actually moving from the valence band. So you got holes over here. Okay. So what we did by adding trivalent impurity to this pure or intrinsic semiconductor, you had actually, at T is equal to 300 Kelvin, okay, room temperature. T is equal to suppose 300 Kelvin, which is considered to be the room temperature, 300 Kelvin. You had EC and EV, and at this particular temperature, semiconductor will have some electrons already in the conduction band, because thermally agitated electrons may move to the conduction band from the valence band. And you got your holes over here. These are the holes, positively charged holes here. So electrons are responsible here in the conduction band for conductivity or for the process of conduction. Holes here in the valence band are responsible for the conduction process. Now, in addition to these, what we got, because we added some trivalent impurity to it and we created some vacated states over here. So there are states, electronic states available in this acceptor state, and the amount of energy required for the electrons to move from the valence band to this acceptor state is very less, which can be actually generated by a very small thermal agitation. So what we got that electrons are actually moved from the valence band to these acceptor states, okay. So that's why you created more amount of holes, actually concentration of holes here in the valence band, okay. And you got the ions over here. These negative charge are now immobile and fixed ions. They will not contribute to the process of conduction, but these holes will, these additional holes that you created in the process of doping of trivalent impurity to the intrinsic semiconductor. So now what you did by adding these group 3 elements to intrinsic semiconductor like silicon or germanium, what you did, you didn't change the electron concentration in the conduction band, but you increase the concentration of holes. If I will write concentration of hole to be P in valence band. Okay, so the same way we did like in n-type semiconductor, we said by adding dopant atoms we are increasing the electron concentration without increasing the number of holes in the valence band. The same way, if you are adding trivalent impurity to silicon or germanium, you are creating more number of holes in the valence band without changing the number of electrons or electron concentration in the conduction band, right? So this is all about your acceptor states or acceptor impurity atoms. Or here we said, so here you can see the concentration of holes here is greater than the concentration of electrons, okay, in the conduction band. So concentration of holes in the valence band is greater than the concentration of electron in the conduction band. So we said P is greater than N, and hence we said this is a p-type extrinsic semiconductor. Extrinsic because we are adding impurity using the process of doping, and p-type because the concentration of hole is more than the concentration of electron. So this is it. Thank you for watching. Please subscribe the channel. Thank you.